All right. So light, we said light is this sort of wave, right? Light does this. But I'm here to tell you, remember I said radio waves? Radio waves and light waves are both types of electromagnetic radiation. So sometimes I abbreviate electromagnetic radiation EM, just for EM. I don't know if I say radiation. Radiation. Okay. So they have things in common, but I'm going to show you, oh, actually right here, this is a figure from a textbook that might come in handy to do the homework, one of the homework that's due on Friday, this figure right here. But when I say cousins of energies, this is what I mean. So let's, and these, you've heard of these before, okay? Like I'm sure you've heard of the Hulk, right? Gamma rays in the Hulk, okay? So the way these are listed, this is the what we say the highest energy, highest E for energy over here, and this is actually the lowest energy, as I have them written, or as they're on here. So other cousins include from gamma rays, we have X-rays, we have ultraviolet or UV, right? UVA, UVB. That's UV stands for ultraviolet. That's why we wear sunscreen. And then we have visible, and actually just this little sector right here in this, what we call it's continuum. Continuum just means it kind of goes, it just, there's no real stop. Infrared, abbreviation, of course, is IR. And then we have microwaves. Sometimes in the morning when I'm using the microwave, I'm like, I think of what it's doing, and basically it's just sending energy through my food to get it going, to make the little food particles vibrate faster. Okay? It's zapping it with energy. Microwaves. And then we have radio waves. Of course, we have FM and AM. So AM are the longest. So the way this works, we've talked a little bit about scientific notation. And so what this figure has is the frequency, that's the number of cycles per second. Okay, so let's just kind of put this in perspective. Gamma rays, number of cycles per second, 10 to the 20th. So I'm going to put a 1. And I'm going to put 20 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, that's how many cycles in 1 second pass a point. Like, all right then. So that's per second. On the other end, let's look at this. Okay, let's look at AM radio waves. So 10 to the 4th is 1 with 4 zeros. Okay, 10 to the 4th per second, or hertz, cycles per second. Well, that's still quite a bit. Okay. All right. So those are all cousins, kissing cousins, I like to say. So the thing about light and the thing about radio waves and the thing about microwaves and the thing about X-rays and the thing about infrared radiation, they what we say propagate through space. So like if you think of a light bulb, think of it just shining in all directions. That's what these radiation energies do. You know, X-rays are not, if you have a source, it's going to go in all directions, okay? By the way, while I'm thinking of it, infrared, where I put IR right here, okay, IR, that is, some of you may know, that's actually heat, or thermal energy. Thermal energy. So it goes in all directions. The word radiate kind of means, like if somebody's radiating, they're like going all directions. But the other thing, so they propagate, the word propagate just means travels. So they travel or radiate in space in all directions. And they're kind of going like this, so they actually have a wavelength, okay? They actually are in a form of a wave, with a wavelength and a frequency and all that. but they're also in these little packets of energy called photons. Now, when we talk about sound traveling through space, sound on Friday looking like this, okay, there are no photons of energy associated with sound, as far as I know. Basically, it's just disturbing the air. Radiation, electromagnetic radiation, not so. It goes like this, okay, and actually tomorrow, one of the things you guys are going to prove is that, I'll kind of give you a precursor. So if it goes like this, what happens, let's see if what happens if I have a picket fence going, I'm going like this, okay, kind of like at a right angle to the floor. What happens if I have a picket fence that's going like this? Okay, I am blocked. And actually tomorrow you are going to block light. You're going to block part of it. So it has a particulate nature and a wave part to it. Okay, how fast do those forms of radiation travel? So all of those cousins, beginning with gamma rays and ending with AM radio waves, okay, all of those radiations travel at what we call the speed of light. They travel at the speed of light, and the variable for the speed of light is the letter C, of course. Okay, but here's the deal. They travel at the speed of light, but what we usually call the speed of light, which is that 300,000 kilometers per second. I know this says 300 million, but that's meters per second. So 300,000 kilometers per second is the speed of light that you may have memorized. I don't know. I have it coming up here in a minute. So speed of light, variable C, is equal to 300,000 km, kilometers per second. So now think about that. You know, kilometer is ballparkish, kind of a mile, okay? Kilometer and mile. So that's a fair piece in 1 second. But I need to qualify this. That means just kind of make sure we're all on the same page. This is the speed of light in a vacuum. So I'll kind of put a little subscript here, vacuum. Okay, speed of light in a vacuum. Here's the deal, this slide kind of talks about it a little bit. These radiations, when they travel through medium other than a vacuum, when you think of vacuum, do you think of, I think of vacuum cleaner. But they talk about the vacuum of space. So the thing about a vacuum means there's no particles, there's no air. So that's the speed it travels in a vacuum. Okay. Now when it travels in other things, and I've got some things that light can travel in, listed up here. Light can travel in air, light can travel in ice, water, some liquids there. Some of these things sound like awesome things to be wearing as jewelry. Okay. So light can travel through all of those. When I say light, remember I'm talking about all different, light and its cousins. It slows down. Okay? It slows down when it travels through anything else like that. So what we come up with is something called an index of refraction. If you're buying a diamond, sometimes they might talk about the index of refraction, just kind of how quality the diamond is. I don't know. It's been so long ago since we bought mine. Okay. So what they do is they take the speed of light and they divide by how fast it's traveling. Calculate by dividing C. So, for instance, if we wanted to know, let's see, where's the diamond? I'll kind of highlight it on here. They went ahead and did the calculation for you. The refractive index for the substance as a medium, the diamond, a diamond. Better not forget my diamond in the thingy over there. That would not be good. There it is. Okay. Wow. Okay. So that means it slows down significantly in a diamond. If you go ahead, what this says is you can take the speed of light, which is this in meters per second, and if you divide by 2.42, okay, which that is the refractive index, Ri of diamond. If you divide that out, you should get this number right here. So notice how much slower it goes in a diamond. And it's that slowing down that makes some of the visual qualities of things that are so cool. Okay. So here I just kind of clean up. What I am used to is not in meters per second, but kilometers per second. I usually kind of think of 300,000 kilometers per second as the speed of light. But if you're going in meters instead of kilometers, that would be the 300 million meters per second. Same thing. All right. So let's work a problem. In order to work this problem, remember you guys get a note card for Thursday, right? You bring a note card with you. I actually, at my desk, reminded myself of this equation up here, okay? The velocity of a wave is equal to the frequency of the wave times the wavelength of the wave, okay? So here we go. Consider red light traveling in air at the speed of light, okay? The frequency is 475 terahertz, which, remember, we're not going to have any metric conversions. With regard to hertz, but we do have the whole calculator thing in scientific notation. So in hertz, that's 4.75 times 10 to the 14th hertz. So if we're kind of like doodling this, or kind of, I don't know about doodling, but just kind of pulling out information, okay, we have the V here, okay, the frequency is 4.75 times 10 to the 14th hertz, okay. So when I look at, if I even put that on my note card, when I look at V of the velocity of the wave is equal to the frequency of the wave times the wavelength, okay, I notice here that I am trying to solve for the wavelength. What is the wavelength? So I would probably rearrange this and get wavelength, but you don't have to. I've kind of seen on your work sometimes you don't rearrange it, which is fine. The wavelength is what? Velocity divided by frequency. And then I'm ready to plug and chug. I actually read that, I think in this, maybe another textbook. It's like they use the words plug and chug. What they mean is plugging into the formula. And chugging is like what you do with your calculator. I don't know. Not drinking a beverage. So wavelength here is that 300 million units for velocity are meters per second divided by the frequency, which is 4.75 times 10 to the 14th hertz. Now, I was thinking about this. If you totally hate scientific notation, you're like, oh, I hate the calculator scientific notation, here's an option for you. That 4.75 times 10 to the 14th, go ahead and unpack it and put those zeros in your calculator. Okay, so that is definitely an option. So I'm going to pack this one up, though. Let's see. 300 million is 3 times 10 to the 8. All right. Let's see what we got. Now, how would we need to round this, do you think? If let's say that the speed of light is just 1 digit, then how do we need to round it? Just 1 digit. I know it sounds bad, but that would be it. I hit 3E8, my calculator, divided by 4.75 EE14. And I got, some of you, I like it when some of you have gotten in the habit of writing down what your calculator displays and then the rounded number. So what my calculator displayed, the coefficient part is 6.3157 3.89 times 10 to the negative, times 10 to the negative 7th. That's what my calculator displays. And we're thinking 1, so all I can do is take that 6. And if that's the case, my answer would be 6 times 10 to the negative 7th. Now, what would the units of wavelength be? Meters, perfect. We good with that? So a teeny little piece of meter. Okay. The next one. Consider radio waves. Now, radio, it's like, in fact, I think there was a question, a homework question, I don't know if I picked it, but radio waves, you think of, oh, I'm listening to the radio. That must be sound, right? Well, it is sound when you listen to it. But for your radio box to get the signal, that's back to a cousin of light. That's back to radio waves. So it can be just a little tricky. So let's do this one. Let's see, what is the frequency? So we're doing after something else. So consider radio waves. They give the wavelength, so I'm going to put the little wavelength is equal to 3.15 meters. Sort of radio waves. Oh, you know what? This problem, and if you had this on the test, I would reiterate, what do you think the speed is? I don't give you speed, but what do you, we're going to go with the same speed as up above. Yep. I would give it to you again. Consider radio waves traveling in air. So we're going to go with the same velocity. The velocity is that 300 million meters per second, or 3 times 10 to the 8th meters per second. And so what is the frequency? So we are after question mark F, frequency. So if we actually kind of look up here and rearrange that, solving for F, I get F is equal to the velocity divided by the wavelength. In this case, the velocity is that 3 times 10 to the 8th meters per second, and the wavelength is that 3.15 meters. I mean, picture that. So here's a meter stick. So like three of these is how long that wavelength is for that radio wave, FM radio wave. Okay, so looks like I can only allow myself one digit again. If I put this in my calculator, 3E8, EE8 divided by 3.15. Wow, I get a big number. Okay, so this is what my calculator displays. Do not write all these down as your answer. I got 9,523,8095, and then I have the decimal. So this is one of those where it looks like if I'm going with just one digit, okay, I'm going to keep that one there. Before I round it, I'm going to go ahead and write it in scientific notation because this is going to drive me nuts. So if I rewrote this in scientific notation, I would move the decimal 1, 2, 3, 4, 5, 6, 7 places. So I got 9.5238 times 10 raised to the 7th power. Okay, now I'm going to round that puppy. And I hate these where I can only have one digit, okay, and it's a 9, and the thing after it is a 5 or greater. So I have to round that 9 up. So I'm going to think through this stepwise. Honestly, it's going to be kind of ugly. So I'm going to round my 9 up, okay? So I'm going to get 10. I'm going to go ahead and put my decimal times 10 to the 7th. I'm not quite done yet. 10 times 10 to the 7th. The reason I did that is it's just easier for me to understand it. Now, what's wrong with this is we have a coefficient of 10, and it's actually supposed to be less than 10. So I can clean this up, and I'm going to go with 1 times 10 to the 8th. Final answer. Again, you know, at this point, throughout this semester for this class, I'm not going to nick you for how you round it. You know better than to write down all those digits. Okay, but that's how you would do that. Now, it's a naked number, so what units do we use for frequency? Hertz. Hertz, don't it? I swear my brother used to do that joke where he's like, you want a donut? I'm like, sure, I'll take a donut. And then he would like hit me in the arm and he'd say, Hertz, don't it? I don't know. Okay. Actually, this slide is good to get to because tomorrow you're going to be doing two kind of, I think they're going to be kind of fast labs with light. One of them is to basically block the light because of how it does this. And the other one is how does light diminish over distance? And this is kind of like a makes sense sort of thing. You know, you guys know that if it's dark outside, you have a street light on, okay? You're right next to the street light. You get all this light from that street light. You get all these photons, all this energy. What happens if you walk away from that light? Okay? Like, there's less energy reaching you. If you go far enough away, actually, that light, and I'm going to try to show you how it's diluted. Basically, I said that light is radiating in all directions. Okay, so like this kind of figure over here says, at this distance we call R, okay, at this distance we call R. Basically, it has a sphere that light is being distributed about like that. Go ahead and now go a second R, the second R. Okay, if you go this far out, okay, that light, now the source didn't change, okay, but the area over which it has been diluted increased. Okay, then again, go this one, we call R3, okay, it's just spread. The same amount of energy from that light is got to get bigger, more and more area like that. So actually the way it works is, and by the way, this works for light and it works for sound. Okay? Sound gets spread in all directions. That's the cool thing about sound. Okay? And it gets diluted as you get farther from the source. So actually, as it turns out, it's a square. The R is how far away you are from the source, and it's raised to the second power of how diluted it gets. So R squared is the dilution that's going on. Since it's getting weaker instead of stronger, we call that an inverse relationship. So that's why, famously, it's called inverse squared law, where it means it's getting more diluted or weaker for the square of the distance. Okay. So in astronomy, it's kind of an important thing because we count on being able to kind of understand how bright a star is by getting a sense for how far away we are from the star. Okay, because we know it's going to follow this inverse R squared law. All right. So another thing in meteorology, I think we'll probably get to, is when we'll talk about severe weather. Are you like me? Do you like it when it's going to thunderstorm? And you're like, yeah. Our dogs don't like it, but I don't know, just something about a good, I even like the thunder. I like the different qualities of thunders. The ones that go, you know they're close, or the ones that go, they're that sound is bouncing off of, so that's why it kind of rolls like that. But if you've heat lightning, okay, sometimes it's a little bit misunderstood. Basically, heat lightning, it happens on hot, muggy nights. That's why they call it heat lightning, I guess. But what's happening is you have a distant storm, okay, you have a distant storm, and for heat lightning, you can see the flashes, but you can't hear it. So it's just this dilution factor. Basically, it's the same thunder that's being created over there, but the thunder gets diluted and doesn't have a chance to get to you, okay? The light has a chance to get to you, okay, but not the thunder. So that's what heat lightning is. So the last topic is an important one, both with regard to sound and light. There is this effect called the Doppler effect, and a good way is if we turn our attention to sound waves, and again we're going to talk about sound waves on Friday. How, remember they're like the longitudinal waves down there? But basically you've probably heard this before, where this little red car is honking its horns. This little red car has horns that's stuck on, okay? As the little red car approaches you, you hear it going, and then it goes past you. Now, one of the things we're going to talk about on Friday is that if you hear something with a high pitch, what that means is you have a short distance between those waves, those rarefications or compressions. Short distance, okay? You have a low tone, you have the long distances between the waves, those sound wavelengths, okay? So the Doppler effect looks like this. That's exactly what the Doppler effect is, okay? So you basically have two things going on. You had, well, a couple things. One is, in this example, we have a moving source. Now, moving source of what? Well, in this case, moving source of sound. What is it? It's the car, okay? Now, the observers are stationary, or in this case, I've actually got two observers. I've got, what this is trying to describe is, let's see, this is you. Okay, so you are, in this case, right here. Okay, and this is your friend. Okay, this is your friend. Can't have too many of those. Okay? So what this is saying is that, notice that the car is going away from you. So basically, can you see where there is a longer distance between those wavelengths? Okay? Longer lambda. Remember, lambda is that. Longer wavelength. That's probably one thing for this unit you're going to want to be able to do. Longer wavelength. Okay? And this means a lower pitch. Okay? And then this one over here, this is a, you probably see, these are shorter wavelengths. And it means a higher pitch. Now, before we move on, though, I want to switch this from, now granted the car needs to be moving, approaching the speed of light, which cars don't move approaching the speed of light. But if something is going fast enough, basically you'll get a color shift. You'll get a color shift. So instead of being a lower pitch, oh, that's one thing I didn't emphasize, darn it. I didn't bring out my poster. I think my poster will show this. So this is the cousin poster. Okay? So this is all the different forms of radiation. One of the things I want to emphasize is if you focus on, visible light, okay, the way this works, you kind of see it, these are the long wavelengths, getting shorter and shorter and shorter. And then here we have visible light right there, visible light, infrared, microwaves, radio waves, ultrasonic, that was kind of the thing I read, right? Okay, up here we have shorter wavelengths, ultraviolet, there's some overlap, X-rays, gamma rays, I have cosmic rays up here. Okay, so these are shorter wavelengths, okay, higher frequency, longer wavelengths, lower frequency. But what I wanted to say is, do you see this right here, visible light? Thank you. If you've ever heard the mnemonic device for visible light, it goes like this. It's like somebody's name. Roy, that's his first name. G is his middle initial. And I've never ran into anybody's name like this. And I always think of the name, or the movie, like Back to the Future with Biff. I know. Okay, anyway, it's been a while. So Roy G. Biv. What that does is each letter stands for a color. So of course we have red, orange, yellow, green, blue, indigo, and I believe this is a right story, and violet. When Isaac Newton first took light, visible light, and made it into the rainbow with a prism, he was like, he didn't like sixes, but he liked sevens. 1, 2, 3, 4, 5, 6, 7. That's right. Okay, there are 7 colors here. To me, indigo. Who talks about indigo, right? Indigo. Well, I don't talk about indigo. But Newton added indigo in to make it 7 instead of 6 colors. All right, so this is the longest wavelength is red. That's my point. And the shortest wavelength is violet. Shortest wavelength. The cool thing about this is and this seems backwards to what I had on the board and stuff like that, the figure from your textbook. But a little bit shorter than violet is UV. Get it? Violet is the shortest color, and right after that, the energy is ultraviolet. I love it. So over here, okay, a little bit longer than red is IR, infrared, bumps up against red. So that's always kind of nice. Yeah. So Roy G. Biv. Anyway, one of the cool things that we see in objects moving very fast is we see a shift in their color. So in astronomy, that's actually a player to understand motion. We can use the Doppler effect to gauge how fast something's moving. Okay? Is that it? Yeah. Okay. So, we aren't going to be doing that tomorrow. But. So here, actually, I printed this out because this looked like a lot of verbs to write down on that. So actually, I have an assignment sheet this time. These are due Friday. And some people wrote the answers on these little assignment sheets that I've given out sometimes, and that's fine. That's cool. What? Illustrated, right? Mm-hmm. So any questions? We'll see you tomorrow in